This is part one of this is part one of the periodic table to atomic theory. In the beginning, you had Democritus, Democritus. He's a Greek philosopher that existed around 460 BC. He postulated the existence of atoms. He said that all atoms are small, hard, indivisible particles. They're made of single material formed into different shapes and sizes. They're always moving, and they form different materials by joining together. We will hear those similar concepts when we get to Dalton, because Dalton will reimagine the same concept that Democritus has, but he will formalize it. So in between the time period of the Greeks and modern chemistry, we have a transformation period called alchemy. And in alchemy, the goal was to take something that was less wanted, so maybe tin, and transforming into something more precious like gold. And so people would sit around and try to figure out, how do you transmutate something into something more desirable like gold? Gold has been wanted by societies ever since the creation societies. We find gold in multiple archaeology evidence. It's shiny, it's a very thin metal, very flaky, it does not tarnish, but in all practicality, it's not useful for many things, but it is one of the monetary systems foundational to what we're talking about. Alchemy existed for about 4 millennia and was on at least 3 continents. So alchemy is our transition zone from Greeks into modern day. So the question that I posed was, if you needed to explain that which you could not see, how would you explain it? For instance, if I have a burning piece of wood, how would you go about explaining why it lost mass? And so many people will start going, well, if I don't have science to prove it, then I say it's magic. And that's along the same terms we're talking about here. So anything that combusted, anything that tarnished, they had a theory called Phlogiston theory. And so it was used to explain that which you could not explain. It became a well-known theory, and so the problem then becomes, how do you disprove a common misconception if people are so poignant on this belief? How do you convince people that phlogiston is not the right idea and that your idea is correct? In comes our scientist. These gentlemen and more start on our voyage to modern chemistry. They start doing it in a meticulous, systematic way. That is what makes it different. So we emerge into modern chemistry, and we have some foundational people that you are responsible for knowing. Joseph Proust, law of constant composition, law of definite proportions, basically states that we know that water is H2O every single time. It has 2 hydrogen and 1 oxygen. Every time we know that. So he just formalized it with law. It was controversial. C.L. Berthollet disagreed with him and really firmly believed in the phlogiston theory. Proust was proven to be correct later on. Priestley is also credited with finding oxygen. You'll find that we have lots of people who are credited with that. Priestley is credited with oxygen. He is a clergyman. Some argue that because he was a clergyman, which also means that he was a priest, that prevented him from debunking the phlogiston theory, because he wanted to believe that there was something superior that would explain all things. Okay? Lavoisier. So the first part is just to let you know how fast chemistry comes on. Chemistry is a very new subject. It is the newest science that we have. So he compiled a list of 23 elements. By the time late in his, I think it's about the time of his death, there were 65 elements that were known. By 1935, there were 88. After World War II, and to now we have 118 technically, and growing. The main thing with him is he constructed a repeatable experiment in which others could obtain his results for oxygen, and that's what made him differently. He disproved the phlogiston theory. This is his experiment. What makes him so phenomenal is the fact that everything is a closed system here, which made him different from everybody else, and that it's repeatable. Somebody else could take his same experiment and repeat it and prove his same results. That's what makes him phenomenal. To us, it doesn't seem like much, but because it's a closed system, because it's repeatable, because you can get the same results, you can do the same math, that's what makes him different. That's why he's the father of chemistry. There are 3 laws that you are responsible for. Law of conservation of matter and energy. It should say matter. Law of conservation of matter and energy says neither created nor destroyed, but transformed. During the 1900s, this law becomes very, very important in the development of the atomic bomb and explains some incredible and phenomenal. Then we had law of definite proportions. Law of definite proportions states that every time that I make something like a compound, it always comes in the same proportion. So water is always 2 hydrogen, 1 oxygen. But I'm not limited just to making water. So when I have hydrogen and oxygen, I'm not just limited to water. I can also make hydrogen peroxide, H2O2. Law of multiple proportions. And then finally, you have Dalton's atomic theory. All matter is composed of small, indivisible particles called atoms. Basically, restate what Democritus has said. Point number 2. For a given element, all atoms are identical in all respects. In particular, all atoms of the same element have the same constant mass, while atoms of different elements have different masses. Point 3. The atoms are the unit of chemical change. Chemical reactions involve the combination, separation, or rearrangement of atoms, but atoms are neither created nor destroyed. Divided into parts are converted into atoms of any kind. That is a restatement of the law of conservation. Point number 4. Atoms combine to form molecules in fixed ratios of small whole numbers. That is a restatement of the law of definite and can also be a restatement of law of multiple proportions. There's a reason this is a theory. It doesn't say Dalton's atomic law, it says Dalton's atomic theory. Point number 1 is true under normal laboratory conditions. That is the key. We know today that an atom consists of protons, neutrons, electrons, and also quarks. But under normal laboratory conditions, that statement is absolutely true. It is point 2 that makes this a false statement. If you look at the periodic table, you will find that the AMU is a decimal number all the way up through 92. Remember, there are 92 natural elements with the exception of a few of them that we've had to make here on Earth because we couldn't find them. But those are decimal numbers. If all the elements, if carbon had the same mass because it was completely identical, then the mass number should be 12.00. But it's not. And it's not because you have isotopes. Isotopes differ by the number of neutrons. Therefore, that is what makes this theory still a theory. Point number 2. Isotopes.